Welcome to today's session. In this problem, we'll be tackling LeetCode number 986, titled Interval List Intersections. This is a fascinating problem that tests your ability to work with intervals and arrays, and it's a great opportunity to sharpen your skills in algorithm design. Let's dive in and explore the problem together. In this problem, you are given two lists of closed intervals, first list and second list. Each interval in first list is represented as start_i, end_i, and each interval in second list is represented as start_j, end_j. The key characteristics of these lists are that they are both sorted in ascending order based on their starting points, and the intervals within each list are pairwise disjoint, meaning no two intervals in the same list overlap. Your task is to determine the intersections between the intervals from first list and second list. When two intervals overlap, their intersection is defined as a closed interval representing the overlapping range. For example, if two intervals, a, b, and c, d, overlap, their intersection will be max, a, c, min, b, d. If there is no overlap between two intervals, the intersection is simply empty. The goal is to return a list of all such intersections between the two given lists of intervals. The output of this problem is a list of intervals that represent the intersections of the two input lists. Let's look at an example to understand this better. Consider first list as 02, 510, 1323, 2425, and second list as 15, 812, 1524, 2526. The output for this input is 12, 55, 810, 1523, 2424, 2525. Here's why: the interval 02 from first list overlaps with 15 from second list, and their intersection is 12. Similarly, 510 from first list overlaps with 15 in second list to give 55. Then, 510 also overlaps with 812 to produce 810. Continuing this process, 1323 intersects with 1524 to give 1523. The interval 2425 intersects with 1524 and 2526 to produce 2424 and 2525, respectively. This process of finding intersections is repeated for all overlapping intervals. Now, let's examine a second example. Here, first list is 13, 59, and second list is an empty list. Since there are no intervals in second list, there can't be any intersections, so the output is simply an empty list. In another example, if first list is empty and second list contains intervals like, for 8, 10, 12, the output is again an empty list because there are no intervals in first list to intersect with those in second list. These examples highlight that if either of the input lists is empty, the result will always be an empty output list, as no intersections are possible without intervals in both lists. For our final example, consider first list as 510 and second list also as 510. Here, both lists contain the same single interval, 510. Since these intervals overlap completely, the intersection is also 510. This example demonstrates that when two intervals are identical, their intersection is exactly the same as the intervals themselves. It also shows that the problem handles cases where intervals overlap entirely, partially, or not at all. By comparing the start and end points of intervals, we can determine the precise range of their intersection, if any. To summarize, let's review the constraints and edge cases for this problem. The lengths of first list and second list can range from 0 to 10⁻⁴, meaning these lists can be very large, so efficiency is important. Each interval is a pair, start to end, where start and end are integers between 0 and 10⁻⁹, and start is always less than or equal to end. All intervals within each list are pairwise disjoint and sorted in ascending order. Key edge cases to consider include one or both input lists being empty, intervals that do not overlap at all, and intervals that overlap partially or completely. Additionally, the algorithm must handle large input sizes efficiently, ensuring that it meets time and space constraints. These conditions ensure the problem is well defined and prepares you to consider a range of scenarios when designing your solution. To tackle the problem of finding intersections between two lists of intervals, we can start by considering a brute force approach. This method involves checking every possible pair of intervals from the two lists to determine if they overlap. For each pair of intervals, say, start_a, end_a, from the first list and start_b, end_b, from the second list, an intersection exists if the intervals satisfy two conditions: start_a must be less than or equal to end_b, and start_b must be less than or equal to end_a. If these conditions hold, the intersection can be calculated as max start_a, start_b, min end_a, end_b. While this approach is conceptually simple, it requires comparing every interval in one list with every interval in the other, resulting in a time complexity of m*n, where m and n are the lengths of the two lists. This makes the brute force method inefficient, especially for large inputs. To improve on this, we can use an optimized approach that leverages the fact that both lists are already sorted by their start times. This is where the two-pointer technique comes into play. In the two-pointer approach, we utilize two indices, I and j, to traverse the two sorted lists simultaneously. At each step, we compare the current interval's first list, I, and second list, j, to check if they overlap. An intersection exists if start_i is less than or equal to end_j and start_j is less than or equal to end_i. When this condition is met, the intersection is determined by taking the maximum of the two start values and the minimum of the two end values, resulting in max start_i, start_j, min end_i, end_j. After processing the intersection, we must decide which pointer to increment. The pointer corresponding to the interval that ends earlier, either end_i or end_j, is moved to the next interval. This ensures that we skip intervals in one list that cannot possibly overlap with the current interval in the other list. The beauty of this approach lies in its efficiency. Each interval is processed only once, giving it a time complexity of m plus n. Moreover, it requires 1 additional space beyond the output, making it highly efficient in terms of memory usage. While other options like binary search or merging the lists were considered, they introduce unnecessary complexity without substantial performance gains compared to this method. The two-pointer approach was chosen as the optimal solution due to its simplicity, efficiency, and the way it naturally leverages the sorted nature of the input. Several key insights contributed to this decision. First, since the interval lists are already sorted, we can process them sequentially without any additional pre-processing, which eliminates extra overhead. Second, the strategy of advancing the pointer of the interval that ends first is critical. This ensures that we skip over intervals that are guaranteed not to overlap, minimizing redundant comparisons and maintaining linear complexity. These observations make the two-pointer approach both intuitive and robust. The real breakthrough here was recognizing that advancing the pointer of the earlier ending interval avoids unnecessary checks entirely, which is what allows us to achieve optimal performance. Additionally, the simplicity of the overlap condition and its calculation makes this approach easy to implement and debug. By avoiding unnecessary pre-processing or complex logic, this method stands out as the most practical and efficient choice. When comparing the available methods, the trade-offs become clear. The brute force approach, while simple conceptually, is prohibitively expensive for large inputs due to its quadratic time complexity. Binary search and merge intervals methods, though creative, add layers of complexity and fail to deliver meaningful performance improvements given the sorted nature of the input. In contrast, the two-pointer approach strikes the perfect balance between efficiency and simplicity. It guarantees linear time complexity by processing each interval only once and avoids unnecessary operations while being straightforward to implement. In conclusion, the two-pointer approach is the definitive solution to the interval list intersections problem. It fully exploits the sorted structure of the input, ensures optimal performance, and keeps the implementation clean and manageable. This makes it the most suitable choice among all considered methods. We are given two lists of intervals, and our task is to find all overlapping intervals between them. Each interval is defined by a start and end point, and we need to identify where these intervals intersect. To solve this, we use two pointers, one for each list, starting at the beginning of both lists. Additionally, we maintain a result list to store the overlapping intervals. As we traverse through both lists, we compare the intervals at the current pointers to determine if they intersect. If an intersection exists, we calculate its boundaries and add it to the result list. When an intersection is identified, we calculate its boundaries. The start of the intersection is the maximum of the two intervals' start points, and the end is the minimum of their end points. If this calculated start is less than or equal to the end, it means we have found a valid intersection, so we append it to the result list. To ensure we process all intervals, we advance the pointer of the list whose current interval ends first. This is because any subsequent intervals in that list cannot overlap with the current interval from the other list. Once one of the pointers goes out of bounds, we stop the traversal and return the result list containing all intersections. This approach is efficient as each interval is processed only once, giving us a linear time complexity. The two-pointer technique is the backbone of this algorithm, as it ensures we traverse both lists efficiently while minimizing unnecessary comparisons. By using two integer pointers, we maintain a constant memory footprint beyond the input and output. The result list is used to store all the valid intersections, and its size depends on the number of overlaps found. We also handle edge cases such as when there are no overlapping intervals or when one or both lists are empty, which results in an empty output. Additionally, the algorithm correctly identifies intersections for cases like fully contained intervals or touching endpoints, ensuring accurate results for all scenarios. This algorithm is both time and space efficient. The time complexity is O, n plus m, where n and m are the lengths of the two lists, as each interval is processed exactly once. The space complexity is O, k, where k is the number of intersections, since these are stored in the result list. Moving to the implementation, the algorithm follows the steps we've discussed: initializing pointers, traversing the lists, calculating intersections, and advancing pointers appropriately. Let's now see how this is implemented in Python. The implementation begins by initializing the pointers I and j to 0 and creating an empty result list. While both pointers are within the bounds of their respective lists, we retrieve the current intervals from each list. We calculate the start and end of the potential intersection, and if the start is less than or equal to the end, we append the intersection to the result list. To process all intervals, we move the pointer of the interval that ends earlier. This ensures we don't miss any intersections while maintaining efficiency. Once the traversal is complete, the result list contains all the overlapping intervals, which we return as the output. To understand the algorithm better, let's walk through an example. Suppose we have two interval lists, 1, 3, 5, 6, 7, 9, and 2, 5, 7, 8. First, we compare 1, 3 with 2, 5, finding an intersection, 2, 3, and advancing the pointer for the first list. Next, we compare 5, 6 with 2, 5, finding another intersection, 5, 5, and advancing the pointer for the second list. We then compare 5, 6 with 7, 8, finding no intersection and advancing the first list's pointer. Finally, 7, 9 is compared with 7, 8, giving the intersection 7, 8. The result list 2, 3, 5, 5, 7, 8 is returned, representing all overlapping intervals. This implementation solves LeetCode problem number 986, interval list intersections using a two-pointer approach. The algorithm efficiently finds overlapping intervals between two sorted lists of intervals. 1. Initialization. We initialize two pointers I and j to 0. These pointers traverse through first list and second list respectively. We also create an empty list result to store the intersection intervals. 2. While loop. The loop runs as long as both pointers are within the bounds of their respective lists. This ensures we process all intervals. 3. Finding overlap. For the current interval's first list, I, and second list, j, we calculate the possible overlap. The start of the overlap is the maximum of the two start times, and the end of the overlap is the minimum of the two end times. If start equals end, it means the intervals overlap, and we append the overlapping interval, start, end, to result. For advancing pointers, to ensure progress in the algorithm, we compare the end times of the current intervals. The pointer corresponding to the interval that ends first is increment. This is because an interval that ends earlier cannot overlap with any future intervals. 5. Output. After the loop completes, result contains all the intervals where first list and second list intersect. The function returns this list. This approach is efficient, with a time complexity of O, m plus n, where m and n are the lengths of first list and second list respectively. The space complexity is O1, as we only use a fixed amount of extra space, apart from the output list. The algorithm handles edge cases, such as empty input lists or intervals that do not overlap, gracefully. Here, we begin by importing the necessary libraries and defining the main class and method. The method, interval intersection, takes two 2D arrays as input, first list and second list, which represent two lists of intervals. We initialize an empty list called result to store the intersections in two pointers, I and j, to iterate through each list. Inside the while loop, we ensure that both pointers are within the bounds of their respective lists. For each pair of intervals, we calculate the intersection by finding the maximum of the two start points and the minimum of the two end points. If the start of the intersection is less than or equal to the end, it means the intervals overlap, so we add this intersection to the result list. To proceed, we move the pointer of the interval that ends earlier to ensure we evaluate all possible intersections sequentially. Finally, after the loop completes, we convert the result list into a 2D array and return it. This ensures our output matches the required format. The method is now complete, and it efficiently computes the intersections of two interval lists using a two-pointer approach. By iterating through both lists simultaneously and only advancing one pointer at a time, we maintain a time complexity of O, m plus n, where m and n are the lengths of the two input lists. This makes the implementation both concise and optimal for solving this problem. To begin solving this problem, we are given two interval lists, first list and second list. The goal is to find their intersections. Here, first list contains intervals 1, 3, and 5, 9, while second list contains 2, 5, and 7, 10. We initialize two pointers, I and j, both starting at 0, and an empty result list to store the intersections. In the first step, we compare the first intervals from both lists, 1, 3, from first list and 2, 5, from second list. The start of the overlap is the maximum of the two start points, which is 2. The end of the overlap is the minimum of the two end points, which is 3. Since the start is less than or equal to the end, we have a valid intersection, 2, 3. This is added to our result list. Since the end of 1, 3 is less than the end of 2, 5, we move the pointer I to the next interval in first list. Now, I is 1, while j remains 0. In the next step, we compare the second interval from first list, 5, 9, with the first interval from second list, 2, 5. The start of the overlap is the maximum of their start points, which is 5. The end of the overlap is the minimum of their end points, which is also 5. Since the start is equal to the end, we have a valid intersection, 5, 5. This is added to our result list. Since the end of 2, 5 is less than or equal to the end of 5, 9, we move the pointer j to the next interval in second list. Now, j is 1. Next, we compare 5, 9 from first list with 7, 10 from second list. The start of the overlap is 7, and the end of the overlap is 9. This gives us another valid intersection, 7, 9, which is added to our result list. Since the end of 5, 9 is less than the end of 7, 10, we move the pointer I. At this point, I exceeds the length of first list, so the loop terminates. The final result is 2, 3, 5, 5, 7, 9. Now, let's consider an example where there is no overlap between the intervals. Here, first list contains 1, 2, and 4, 5, while second list contains 6, 7. We initialize I and j to 0 and start with an empty result list. First, we compare 1, 2 from first list with 6, 7 from second list. The start of the overlap is 6, and the end of the overlap is 2. Since the start is greater than the end, there is no valid intersection. In this case, we move the pointer I to the next interval in first list because the end of 1, 2 is less than the start of 6, 7. Now, I is 1, and j remains 0. Next, we compare 4, 5 from first list with 6, 7 from second list. The start of the overlap is 6, and the end of the overlap is 5. Again, the start is greater than the end, so there is no valid intersection. We move the pointer I to the next interval in first list because the end of 4, 5 is less than the start of 6, 7. Now, I is 2, which exceeds the length of first list, so the loop ends. Since no intersections were found, the final result is an empty list. In this third example, we examine fully contained intervals. Here, first list contains one interval, 1, 10, and second list contains three intervals, 2, 3, 4, 8, and 9, 12. We initialize the pointers I and j to 0 and start with an empty result list. First, we compare 1, 10 from first list with 2, 3 from second list. The start of the overlap is 2, and the end of the overlap is 3. This gives us a valid intersection, 2, 3, which is added to the result list. Since the end of 2, 3 is less than the end of 1, 10, we move the pointer j to the next interval in second list. Now, j is 1. Next, we compare 1, 10 from first list with 4, 8 from second list. The start of the overlap is 4, and the end of the overlap is 8. This gives us a valid intersection, 4, 8, which is added to the result list. Since the end of 4, 8 is less than the end of 1, 10, we move the pointer j to the next interval in second list. Now, j is 2. Finally, we compare 1, 10 from first list with 9, 12 from second list. The start of the overlap is 9, and the end of the overlap is 10. This gives us another valid intersection, 9, 10, which is added to the result list. Since the end of 1, 10 is less than or equal to the end of 9, 12, we move the pointer I. Now, I exceeds the length of first list, so the loop ends. The final result is 2, 3, 4, 8, 9, 10. When analyzing the time complexity of this algorithm, we start by considering the input, which consists of two lists of intervals, first list with length m and second list with length n. First, the initialization of pointers I and j, as well as the result list, takes constant time, or O1. Next, the main computational workload occurs within the while loop. This loop iterates as long as neither pointer reaches the end of its respective list. Each iteration processes one pair of intervals, performing constant time operations such as calculating the intersection using the max and min functions, checking if an intersection exists, and possibly appending it to the result list. Additionally, advancing the pointer associated with the interval that ends first is also a constant time operation. Since either I or j advances in each iteration, the total number of iterations is proportional to the combined lengths of the two lists, m plus n. Finally, returning the result list is a constant time operation. Therefore, the overall time complexity of the algorithm is O, m plus n. Now, let's examine the space complexity. The input lists first list and second list are provided as inputs and do not require additional memory allocation, so they do not contribute to the algorithm's space complexity. The result list, on the other hand, stores the intersections of the intervals. In the worst-case scenario, where every interval in first list intersects with every interval in second list, the size of the result list is proportional to the smaller of the two input sizes, or O, min, m, n. Furthermore, the algorithm only uses a few additional variables, such as the pointers I and j, and temporary variables like start and end, all of which require constant space, or O1. Combining these factors, the overall space complexity of the algorithm is O, min, m, n. To put this analysis into perspective, consider the brute force approach as a point of comparison. A naive solution would compare every interval in first list with every interval in second list, leading to a time complexity of O, m*n, due to m*n comparisons. However, the space complexity would remain O, min, n, since the storage of intersections depends only on the smaller list size. In contrast, the optimized approach, which leverages the sorted order of the input lists and uses two pointers to traverse them efficiently, achieves a significant improvement in time complexity, reducing it to O, m plus n. This improvement is achieved by avoiding unnecessary comparisons and redundant checks. For best-case scenarios, such as when one of the lists is empty, the algorithm terminates immediately, requiring only O1 time and space. In the average case, it processes all intervals in both lists, maintaining the time complexity of O, m plus n, and space complexity of O, min, m, n. Even in the worst case, where every interval in first list intersects with an interval in second list, the algorithm still runs efficiently with the same time and space complexities. Finally, let's solidify the reasoning behind these big O bounds. The two-pointer strategy ensures that each interval is processed in constant time, as each pointer increment in comparison is an O(1) operation. Since the while loop iterates at most m plus n times, the overall time complexity remains O(m plus n). On the space complexity side, the dominant factor is the result list, which stores the intersections. The number of intersections is bounded by the smaller of the two input sizes, leading to a space complexity of O(min m n). This combination of time and space analysis confirms that the algorithm is both efficient and optimal for the problem, adhering to these well-defined big O bounds. When working on interval problems like this, there are a few common mistakes to watch out for. First, handling edge cases incorrectly is a frequent issue. For example, you might overlook scenarios where one interval is completely contained within another or when intervals don't overlap at all. This can lead to incorrect results or even runtime errors, such as out-of-bounds issues. Another common pitfall is comparing the wrong interval boundaries. You might mistakenly compare the end of one interval with the end of another, when the correct comparison should involve the start of one interval. This can cause you to miss valid intersections or introduce logical flaws in your algorithm. Additionally, while the input lists are usually guaranteed to be sorted, it's important to verify this assumption. If you forget and either skip sorting or sort unnecessarily, your logic may break. Infinite loops are another risk, especially in pointer-based solutions. If you don't increment the correct pointer, or worse, update both pointers simultaneously, you could end up with infinite loops or skipped intervals. Finally, avoid overcomplicating your solution. Some candidates try to preprocess or merge intervals unnecessarily, which can increase the complexity to O(n squared), or worse, when simpler linear approaches would suffice. Now, let's talk about some key insights to keep in mind during interviews. The two-pointer pattern is a powerful technique for solving interval-related problems efficiently. You should feel comfortable iterating through two sorted lists while managing the logic for advancing pointers correctly. It's also essential to focus on efficient comparisons. Remember, two intervals overlap if the start of one interval is less than or equal to the end of the other, and vice versa. These conditions are fundamental and can help you simplify your logic. Always account for edge cases, such as empty input lists, intervals that don't overlap at all, or those that only touch at their boundaries without overlapping. Finally, communication is critical in an interview. When explaining your solution, walk through your thought process clearly, especially for tricky edge cases like nested intervals or touching boundaries. This not only demonstrates your understanding but also helps the interviewer follow your reasoning. You might also encounter related problems that build on similar concepts. For instance, LeetCode 56, merge intervals, involves combining overlapping intervals into a single interval, while LeetCode 435, non-overlapping intervals, focuses on removing intervals to ensure no overlaps remain. Another relevant problem is LeetCode 1288, remove covered intervals, which asks you to identify and remove intervals that are completely covered by others. Understanding these variations can deepen your grasp of interval problems. Now, in terms of approaches, the brute force method is the simplest to understand. This involves checking every pair of intervals to find overlaps. While straightforward, its O(n*m) complexity makes it inefficient for large inputs. On the other hand, the two-pointer approach is much more efficient, leveraging the fact that the lists are sorted. By iterating through both lists with pointers, you can find intersections in O(n plus m) time. However, this method requires a clear understanding of pointer-based logic to avoid mistakes. The sweepline algorithm is another alternative, though it's less commonly used for simpler problems like this. In this approach, you treat the boundaries of intervals as events and process them in sorted order. This involves sorting all the interval boundaries, which introduces a complexity of O(n plus m) log n plus m. While this method can handle more complex variations of interval problems, it's often overkill for straightforward tasks like interval intersections. The trade-offs here involve balancing the additional complexity of sorting against the specific constraints of the problem. For simpler cases, the two-pointer technique remains the most efficient and practical choice. Great job on making it to the end. To recap, we walked through the problem, discussed an efficient approach, and highlighted some key insights along the way. Remember, mastering interval problems like these can significantly improve your algorithmic thinking. Thank you for joining, and I encourage you to keep coding and exploring more problems. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!